Hello, we have talked much more about the electronic properties and the solve the problems. But in today's videos, I will solve some problems related to the magnetic properties of materials. Hope this will help you in understanding the problems and the concepts. Welcome to Material Horizon. See you after the intro. On today's topic, we won't be discussing much about the theories, rather, we will solve the problems. We might discuss about theory in some other videos. So, let's start with the problem. First problem: a paramagnetic material has a magnetic field intensity of 10 to the power 4 ampere per meter. If the susceptibility of that material at room temperature is 3.7 10 to the power minus 5, calculate the magnetizations and flux density in the material. First of all, this is a paramagnetic material, so I won't be going that much details, but some initial things we should know that these materials are actually weakly attracted to magnets. Okay, and they do not retain any magnetization or magnetic property, you can say, in the absence of external magnetic field. So it means when the external magnetic field is removed, it will lose all its magnetic property. So what are those materials? I can take some example like magnesium, molybdenum, tantalum, as well as lithium. Okay. So in this problem, it is giving that the field intensity H, field intensity given by H, is given by 10 to the power 4 ampere per meter. This unit should be very cautiously dealt with. What is the susceptibility? Before that susceptibility, you should know that is the degree to which the magnetic materials can be magnetized. My mistake, that any material can be magnetized. The degree, so it is the degree to which any material can be magnetized. Okay, and it has different value, like this is greater than 0 for paramagnetic, and it is less than 0 for diamagnetic. So basically this determines whether a material is attracted or repelled by the magnetic field. However, this chi is given by, coming to the problem, chi is given by m by h. This is actually magnetization and this is magnetic field intensity. So now I am not going to the details of each parameters here. This m is actually equal to h into chi. So this h is given 10 to the power 4 and chi is given 3.7 10 to the power minus 4. As it is a ratio of these two magnetic property, doesn't have any unit. Okay. So what is the m finally? Finally m is 37 ampere per meter. This is magnetization. So ultimately, what is flux density? So flux density is given by a parameter is B, that is actually equal to mu naught into M plus H. This means free permittivity in free space. This is magnetization and this is magnetic intensity. Field intensity. So this field intensity, when it is added with some the magnetization of this is a material property, and ultimately the total flux density, or it can be also called as induced magnetization. So this is a summation of these two parameter when we multiply with unit, and mu naught is 4 pi into 10 to the minus 7, that would be given, I guess, and 37 plus 10 to the 4. So ultimately it is coming 0.126 Weber per meter square. So this is the final magnetic flux density. Okay, I think it is clear now. Okay, so then going to the next problem, what they are saying, a magnetic material has a magnetization of 2300 ampere per meter, produces a flux density, so B is given here, and this is magnetization M is given. So the relative permittivity, so we were talking about the permittivity of free space, that was mu net, and relative permittivity is mu r. So here two parameters are given, as I have seen, 200 ampere per meter. B is actually 0.00314 Weber per meter square. Now what is B? We were previous equations we were talking about mu naught into M plus H. Okay, so if by this equation if we rearrange, then H would be B by mu naught minus M, and that would be 0.00314 divided by 4 pi 10 to the power minus 7 minus 2300. Okay, so from there we will get H equal to 198.732 ampere per meter. So this is the field strength. Okay, so we got the field strength, right? So now we want to have what is the relative permittivity. So if we actually work with this equation, we will get relative permittivity, because this B is given by mu r into mu naught into H, because it is proportional to the magnetic field externally applied, and this is as usual, I'm just multiplying them. And if I want to have mu r, what we will do, I will take this side. Okay, so mu naught into H will be common, and that would be mu r minus 1. This would be mu naught into M. So this mu naught will be cancelled out, and we will have this mu r minus 1 equal to M by H. Okay, so we have the M, we have the H, so we will have mu r. So mu r equal to M by H plus 1. So this is equal to 198.7326 plus 1. So we will come to an end where mu r is 12.573, and mu r is also unitless, and because that is also relative permittivity. Okay, ratio of materials permittivity to the permittivity of free space. Okay, moving on to the next problem. A paramagnetic material, again paramagnetic material, has a BCC structure with a cubic edge So cubic edge, so here a lattice parameter is given 2.5 angstrom. Okay, very common, that is 2.5 10 to the power minus 10 meter. If the saturation value of magnetization is 1.8 into 6 ampere, so that is the maximum value possible. Okay, that is why saturation value of magnetization. Calculate the magnetization contribute per atom in Bohr magneton. So I have to have the unit in Bohr magneton, not like Weber per meter square or all those units. We want to have in Bohr magneton. Correct. So first of all, we will go step by step. It's a tricky, but yeah, not that difficult. M is given here also 1.8 10 to the power 6 ampere per meter. Okay. So now what we have to calculate, because we see here that it is saying about per atom. I mean, so for that we first what we have to have, that is the number of atoms in unit volume. So in other sense, the atomic density. So number of atom per unit volume. So the unit will be in meter minus 3, right? Okay. So that would be like, if I write it n, so the number of atom would be 2 for BCC structure. Okay. So here each atom at the corner will be shared by 8 atoms. So there are total 8 corners. So 8 into 1 by 8. So there will be 1 plus 1 atom at the center. So that will be also added with 1. So ultimately 2 atoms. Okay, so 2 atoms. So I want to have per unit volume. So that's why it would, at the bottom, the numerator, there would be a cube. So 2.5 10 to the minus 10. So that to determine the volume of the unit cell. So ultimately what we have, 1.28 10 to the power 29 per meter cube. So next, magnetization now produced by per atom. Magnetization produced per atom. So M per atom is total magnetization is, that is given in the problem, 10 to the power 6 divided by the number of atoms, 28 into 10 to the power 29. So ultimately it will give rise 1.40 into 10 to the power minus 23 ampere per meter square. So now we have got the answer that what is the magnetization per atom. But the question, in the questions they are asking, this should be in Bohr magneton, not ampere per meter square. So for that, what we have to do, we have to get what is the value of Bohr magneton in ampere per meter square. And if we divide it, then we will easily get the unit in Bohr magneton. So before that, if I know the value of Bohr magneton, then that is okay. If I don't know, then we have to calculate, and the calculate is not that difficult calculation. So Bohr magneton mu b is given by EH by 4 pi m, and these are all electron, Planck's constant, and this is the mass of the electron. So if we put them together, we will get 10 to the power minus 24 ampere per meter square. So this is for per Bohr magneton, it has a value of this, right? So now what is the M per atom? Now it is easy, just simply if we divide, we will get the answer 9.27 into 10 to the power minus 24. Okay, so ultimately what do we get? 1.519 Bohr magneton, or sometime it is written like 1.519 mu b. Okay, so these are the three important problems generally we encounter in many exams. So it may come in different forms, but this is the pattern. Okay, three important patterns in competitive exam. However, we will be talking much more about problems and theories in the next video, and that's it for this video. Thank you for watching the video. Today I have discussed three of the basic problems comes under magnetic properties of materials. Uh, I will also solve some other problems and give you some concepts related to these problems in later videos. Uh, and again, thank you, and please subscribe and like the video, and see you in the next video.